Hey there, I'm your guide through the fascinating world of calculus today. We're diving into how we use calculus, specifically definite integrals, to calculate the volume of 3D objects formed by rotating a 2D curve. This might sound a bit complex, but trust me, I'll make it as simple as pie. Or should I say, as simple as pi. Let's start with the basics. Solids of revolution sounds like something out of a sci-fi movie, right? But it's actually a term in math that describes shapes formed by spinning a curve around an axis. Think of it like spinning clay on a potter's wheel to create a vase. The shapes you're familiar with, like cylinders, cones, and spheres, are classic examples of these solids. Now, how do we calculate the volume of these cool shapes? Here's where it gets really interesting. We use a formula involving definite integrals. Let's break it down with an example, say, calculating the volume of a cylinder. Imagine you have a line segment that represents the height of the cylinder, and you rotate this around one axis. The function describing this line segment could be as simple as fx equals sine h, where h is the height. If this line segment is rotated from x equals sine 0 to x equals sine r, where r is the radius, we can set up our integral to calculate the volume. Using the definite integral, the volume v is calculated as v equals sine pi times the integral from 0 to r of dx. Solving this gives us ph squared r, which matches the familiar volume formula for a cylinder, the area of the base times the height. And just like that, calculus confirms what we already know through simpler geometry. But why should you, as a computer science student, care about this? Well, understanding the volume of solids of revolution is super important in fields like computer graphics, modeling, and simulation. Whether you're designing the next blockbuster video game or simulating physical phenomena, calculus helps you create more realistic and mathematically accurate 3D models. In conclusion, mastering the use of definite integrals to calculate volumes isn't just about solving math problems. It's about building a foundation that will support your work in various computational fields. It enhances your problem-solving skills and prepares you for more complex challenges ahead. So, keep at it, and soon, you'll see just how much calculus can do in the digital world. And that's a wrap on how calculus helps us calculate 3D volumes. Thanks for sticking with me, and I hope you found this as exciting as I do. Keep exploring, keep calculating, and remember, math is the language of the universe, and you're becoming fluent in it.